Jai Hind, dear students. Today we will discuss one more important topic of electronic devices, that is junction capacitance, right? So this is from third unit topic, junction capacitance. So as we know, the diode can behave like a capacitor at higher frequencies. So first of all, we will see the construction of diode, how we can draw the depletion layer, how we can show the charge density, how we can show the electric field and voltage with respect to depletion layer and with respect to distance, and then we will see how we can calculate or how we can prove that diode will behave like a capacitor, right? So we will drive the relation, or we will try to find out the value of the capacitor or diode, right? So first of all, if I show if I draw the PN junction diode, the structure of the PN junction diode. So here we have one side we have P type semiconductor, one side we have N type semiconductor, and in between we have depletion region. So suppose this is your depletion region, this is your depletion layer, right? And here I have, this is our junction, here I have negative ions on P side, and similarly here on N side we have positive ions, right? So if I draw the charge density, draw the charge density, so here I can assume this is minus Wp, this is Wn, and here this is 0. So here I can say here x is 0, x is equal to minus Wp, and here x is equal to Wn at this end. So if I draw the charge density, so here charge density we can represent it by rho, and with respect to distance we can draw it. So it will be like this, total negative charge, and here we will show the total positive charge, right? So this is negative charge and this one is positive charge, right? This is charge density, and using Poisson equation, that is dE over dx is equal to rho upon epsilon. This is Poisson equation. Using this I can also draw the electric field with respect to distance. So how can I show? This will be the electric field here at minus omega p or minus Wp and plus Wn, electric field will be 0, and at x is equal to 0 the electric field will be maximum. Suppose this is Em, the value of this electric field at x is equal to 0 is Em, right? Similarly, we can show the potential, also. So the potential will be like this, here the potential will be Vn and here the potential will be Vp. So by this way we can represent, okay. Now if I assume that the doping on the P side is higher than the doping on the N side, that means we have P positive N combination. Doping on P side is very higher than the doping on N side. So what will be the effect of doping on the depletion region? The depletion region will be narrower on the P side as compared to N side, right? So if I say that Na is very greater than Nd, Na is the acceptor atoms impurity and Nd is the donor atoms impurity, impurity concentration. Na is the acceptor impurity concentration, right? So if Na is very greater than Nd, so in that case Wp will be very less than Wn. That means depletion region on P side will be very small as compared to the depletion region on N side, right? So this total depletion region W is Wn plus Wp, and what we have considered? We have considered that Wp is very less than Wn, so we can say W will be approximately is equal to Wn. So with this approximation, if I move, then we can redraw these diagrams, right? So for this if I redraw with the assumption that W is approximately is equal to Wn. Assumption is W is approximately is equal to Wn, right? And now if I draw the diagram, so here I have P side, this is P side, this is P side, this is N side. On P side, this is your depletion region now. On P side, we have negative ions in the depletion region, and on N side we have positive ions, right? There is no charge carrier available in the depletion region. Okay. So what we are trying to prove, that diode can behave like a capacitor. So if I assume this P side is behaving like a conducting plate, again this N side is behaving like a conducting plate, and this depletion region is behaving like a dielectric. Why dielectric? Because there is no charge carrier available in the depletion region. So we can say it will behave like a dielectric. So P side is one conducting plate, N side is another conducting plate, and there is dielectric in between them. So we are considering that this structure is very similar to the capacitor, right? So this PN junction diode should behave like a capacitor. Okay. So what we are trying to do, first we will draw the diagrams for the charge density, for the electric field, and for the potential, right? Again here we have minus Wp, this is Wn, and here x is equal to 0, and total width is W. Total width is W. Okay. Now if I draw the charge density, this is distance x, here we can take the charge density rho. So again it will be like this. So here we will have total negative charge, and here we have total positive charge. With Poisson equation, using Poisson equation, we can draw the electric field also. So electric field will be, we can draw like this. So in this case, as we have assumed that W will be approximately is equal to Wn, so electric field will be like this. So Wp, Wn, again here x is equal to 0, and this is the maximum value, suppose this is Em. In similar manner, we can draw the potential also. So this will be the potential, and here the potential, as we have assumed that omega this W is approximately equal to Wn, so here this potential will be is equal to Wb. This is potential graph. Here x is equal to 0 again, right? So now if we classify the diode capacitance, as we can bias a diode in two types. We can either forward bias it, or we can either reverse bias it. So there are two biasing methods for a diode. So we can say we can classify the diode capacitance in two types, right? So diode capacitance can be classified in two types. One is transition capacitance, and another one is diffusion capacitance. Diffusion, or we can say storage charge capacitance. Diffusion or storage charge capacitance. So there are two types. So transition capacitance we denoted it by Ct, and this diffusion capacitance we denote it by Cd. So first of all we will discuss the transition capacitance, right? So first of all we will discuss the transition capacitance. Transition capacitance Ct. It generally occurs in reverse bias. Okay, it generally occurs in reverse bias, right? And we know that the capacitance, the value of capacitance can be given by C will be is equal to dq by dV, where we can say, we can define the capacitance as rate of change of charge with respect to voltage. So C should be is equal to dq by dV, right? So this is suppose equation number 1. Now what is the Poisson equation? Poisson equation is d square V over dx square is equal to minus rho upon epsilon. What is rho? Rho is a charge density. Okay. So what we have considered? We have considered W is approximately is equal to Wn. right? So this charge density can be written as minus q into Nd upon epsilon, right? Now if I integrate this equation, after integrating, what I will get dv by dx, and it will be is equal to minus q into Nd upon epsilon into x, right? When we are integrating, so we are taking constant C1 here, right? So C1 constant we have to consider. Now if we apply the boundary condition, we can find the value of this C1. So what boundary condition we have to apply? First of all, if I consider this is equation number 2, then I can write this equation as this will be is equal to minus E, because we know electric field E will be is equal to minus dV by dx, right? So I can write dV by dx is equal to minus E, it will be is equal to minus q into Nd into x divided by epsilon plus C1, right? Now at x is equal to 0, at x is equal to 0, at x is equal to Wn. First we will take at x is equal to Wn. At x is equal to Wn, this electric field is 0. Here we can see at x is equal to Wn, this electric field is 0, right? So at x is equal to Wn, electric field will be 0. So if I apply these boundary condition in above equation, so it will be 0 is equal to minus q Nd upon epsilon into Wn plus C1. And what we have assumed? We have assumed that Wn is approximately is equal to W. So I can write it as 0 is equal to minus q Nd upon epsilon into W plus C1. So what will be the value of C1? C1 will be is equal to q Nd upon epsilon into W. This will be the value of C1. So if I put this value in this equation number 2, so I can write dV by dx is equal to minus q Nd into epsilon, minus q Nd upon epsilon into x minus q Nd upon epsilon into x plus C1 is equal to q Nd into W upon epsilon, right? This equation can be rewritten as dV by dx is equal to, I can take minus q into Nd upon epsilon, I can take this common, and inside will be x minus W, right? Now if I further integrate this equation, so after integrating, what I will get? V is equal to minus q Nd upon epsilon. So here again we are integrating it. After integration we are getting this. So V is equal to minus q Nd upon epsilon into x square by 2 minus W into x plus another constant, that is C2, right? So after integration I will get this. Now I have to find the value of this C2 by applying the boundary conditions. So what boundary condition I can apply? I can apply that at x is equal to 0, this V is 0. Here we can see in this diagram, at x is equal to 0, this V is 0. So if I apply this condition, then suppose this is equation number 3. So from this equation, what we will get? So if we put V is equal to 0 and x is equal to 0, C2 will be 0. So with these boundary conditions, we can get C2 is equal to 0. So again I can put this value of C2 in equation number 3, and V will be is equal to minus q Nd upon epsilon into x square by 2 minus Wx, x square by 2 minus W into x, right? Now at x is equal to Wn, this V will be is equal to Vb. Again we can see in this diagram, at x is equal to Wn, this V will be is equal to Vb, right? So Vb is nothing but the barrier potential. It is nothing but the barrier potential, So generally this VB is equal to Vn minus Vp, but here we are considering that the depletion region on the P side is very narrow. So this VB will directly be is equal to the Vn, we can say. Okay, so the voltage at the edge of this depletion region on the N side, this will be that will represent the directly represent the barrier potential. Okay, so V will be is equal to VB at X is equal to Wn. So if I use this value, so this VB will be is equal to minus Q ND upon epsilon into, and in place of this Wn I can write W only, because we have considered W is approximately equal to Wn. So I can write W in place of X. So here I can write W square by 2 minus W into W, right? After solving this, I will get plus Q ND upon epsilon into W square by 2, right? So this will be the value of VB. But now here we have assumed that the transition capacitance, we are considering the transition capacitance in case of reverse bias, but till now we have not taken the effect of reverse bias. So we will add the reverse bias voltage in this equation. So after adding the reverse bias voltage, this equation will be VB plus VR. VB is the barrier potential and VR is the reverse bias voltage. So VB plus VR is equal to Q into ND upon epsilon into W square by 2, right? So from this equation I can find the value of W square. So this W square will be 2 epsilon into VB plus VR divided by Q into ND, right? So this equation I will get. So this is equation number 4. This is your equation number 4, right? Now I have total charge Q can be written as Q into ND into W into A. Okay, so I want to find out the value of capacitance CT. CT is equal to dQ by dVR in case of reverse bias, right? So it should be the value of the transition capacitance CT. So if I differentiate this with respect to VR, so what I need, so if I differentiate it with respect to VR, so this should be modified to dW with respect to dVR into A. So what I need this value. To find this dQ by dVR, I need dW by dVR. I have the value of W square from equation 4. I have the value of W square. So W square, I know W square is equal to 2 epsilon VB plus VR, 2 epsilon VB plus VR divided by Q into ND, Q into ND. If I differentiate this with respect to VR, so what I will get? So 2W into dW by dVR is equal to, here we will get 2 epsilon upon Q ND, right? So to find this value dW by dVR, we can rearrange the terms and it will be 2 epsilon upon Q ND into 2W. So this 2 will be cancelled out by this. So final value will be epsilon upon Q ND into W, right? I can use this value, I can put this value in this equation. So from here I will get dQ by dVR and it will be is equal to Q ND into this value. This is epsilon upon Q ND into W into A. So this Q ND will be cancelled out and final value will be dQ by dVR, it will be is equal to epsilon A upon W, epsilon A upon W. And what is this? This is nothing but the value of the capacitance CT. CT will be epsilon A upon W. So this expression, we are familiar with this expression. This is the normal expression that we express for the capacitor. So here the CT is equal to epsilon A upon W, and what is W? A is the area of the junction and what is W? W is the depletion width. So in case of reverse bias, this depletion width will increase and this transition capacitance will decrease. So this is the value of the transition capacitance in reverse bias. And these capacitance, transition capacitance, either we can take diffusion capacitance. These capacitance are active only on the higher frequencies, because at lower frequency the value we can find the capacitance impedance of the capacitor. So XC is equal to 1 upon 2 pi FC. We are familiar with this equation. At lower frequencies, this XC will show the behavior of open circuit, or it will be it will behave like an open circuit. And for higher frequencies, there will be a finite value of XC. So if I draw the equivalent circuit, suppose this is diode, and here if I show the capacitor, if I show a capacitor here in the parallel of this diode, so this diode will be available only at the higher frequencies. At lower frequencies, this will not be available. This will be open circuited, right? So at higher frequencies, we have to consider these capacitances. So the value of transition capacitance will be CT is equal to epsilon A upon W. So this is one capacitance that we are considering in the reverse bias condition. Okay. Second case, second capacitance we can take, that is, second capacitance is the diffusion capacitance. The diffusion capacitance, or we can say storage charge capacitance. Diffusion capacitance or storage charge capacitance. So we generally denote it by CD. So and this capacitance we consider in forward bias. This capacitance we consider in forward bias. So obviously here we can conclude that we can say that in case of forward bias, the width of depletion region will be very narrow, or will be very small as compared to reverse bias. So this capacitance value of this capacitance CD will be higher than CT. So we can say that this CD will be very higher than CT, because this is the capacitance in case of forward bias and this is the capacitance in case of reverse bias, right? So we have to find the value of this CD also, right? So we are assuming that the junction is initially in forward bias, right? And we know in case of forward bias, the current flow due to the majority charge carrier. Majority charge carriers on the P side, we know holes are the majority charge carrier on the P side, and electrons are the majority charge carriers on the N side. So in forward bias, the current is flowing due to these majority charge carriers. And we also know that the majority charge carriers can easily cross the junction, in forward bias, right? So assume the diode is in forward bias and few majority charge carriers are crossing the junction. They are in between the depletion region, and suddenly we change the biasing and we change it from forward bias to reverse bias. Suddenly we are doing it. So what will happen? Few charge carriers, those are the majority charge carriers, they will stuck into the depletion region. This condition is called, we call storage charge capacitance, because we are considering the charge is stored in the depletion region. These are the majority charge carrier, which in the case of forward bias, they are crossing the junction and suddenly we change it to reverse bias. So this those charge carriers are stuck into the depletion region. That's why we are considering that the charge is stored in the capacitor, okay, and this condition is called storage charge capacitance. Now what we have to do, because we have applied reverse bias, so with reverse bias voltage, what will be the rate of change, rate of change of this charge, because this charge will try to come out from the depletion region. So what will be the rate of change of charge with respect to reverse bias voltage? This is called the diffusion capacitance, right? So how we can find the value? We know the simple relation that I is equal to Q upon, generally we have studied T, but here we will not take T, we will take this, I is equal to Q upon tau. What is tau? Tau is the average lifetime of the charge carrier. Here tau is the average lifetime of charge carrier. Average lifetime of charge carrier. Or if I want to find out this charge, so Q will be equal to I into tau, right? We are considering this is the capacitance of forward bias. In case of forward bias, I know this I can be given as I is equal to I naught e to the power Vd upon eta Vt minus 1. So this is the equation, right? Now if I differentiate this equation with respect to voltage, so I can write di, or first if I put the value in this q, so what will be q? Q will be I naught tau into I naught e to the power Vd upon eta Vt minus 1. So this I can get. Now if I differentiate this with respect to voltage, so what will be dq by dv? It will be tau into I naught divided by eta Vt and e to the power Vd upon eta Vt, right? Now again if I use this equation, what I can write? I is equal to I naught e to the power Vd upon eta Vt minus I naught, right? Take this I naught on this side, so it will be I plus I naught is equal to I naught e to the power Vd upon eta Vt, right? So this value is equal to I plus I naught. Here I have this value, same value, I naught into e to the power Vd upon eta Vt. So I can replace this value with I plus I naught. So from this equation I can write dq by dv is equal to tau into I plus I naught upon eta Vt. I can write this, right? Now as I know that I is very greater than I naught, because I is the forward current, forward bias current, I naught is the saturation current, right? I generally we can take in milliamperes, and this saturation current is very small, we take it in microamperes, right? So I can neglect this I naught. So this dq by dv will be is equal to tau into I upon eta Vt, and this is nothing but rate of change of charge with respect to voltage. So this is the value of CD, that is diffusion capacitance. So CD will be is equal to dq by dv, and it will be is equal to tau into I upon eta Vt. So finally we can say CD or diffusion capacitance will be is equal to tau into I upon eta Vt, right? So this is the value of the diffusion capacitance. So this is the way how we can calculate the value of transition capacitance, how we can calculate the value of diffusion capacitance. So this is a very important topic. And if we try to plot these capacitance with respect to voltage, so what graph we will get? So here if I take the capacitance and here on this axis I take the voltage, right? So I will get this type of graph, and here this side I will get the depletion. Here on this side I will get, because in forward bias we have depletion capacitance. So here this side we will have depletion capacitance, we will have diffusion capacitance. Because in case of forward bias the voltage will be positive, and in case of positive voltage or in case of forward bias the capacitance is diffusion capacitance. So this will be diffusion capacitance, right? And here on this side in case of reverse bias, because the voltage is negative, so we can say this is the case of reverse bias and capacitance is also decreasing. Here we will have transition capacitance. This transition capacitance is also called depletion capacitance. It is also called junction capacitance. And this diffusion capacitance is also called storage charge capacitance, right? So this graph we will obtain, or we can say this is the curve between the capacitance and the voltage, right? So this is all that I want to discuss in this topic. Thank you.